Guys, ready?
Yep.
Here we go.
Let's do it.
Welcome, ladies and gentlemen, to another webinar in DRYDEN Aqua Water Treatment. My name is Dominic. I'm the CEO of the group, and today we are talking about filters, really about the hardware. Here are my two colleagues.
Yeah, Mike Domain, have a long history in aquarium and aquaculture, 25 years, and studied oceanography as a trade.
I'm Jesus Barriuso. I have a PhD in mechanical engineering, and I come from Calplast. We have been manufacturing filters for 50 years for swimming pool, water treatment, aquarium, and so on.
We are a very international group. You come originally from South Africa, you from
correct.
Spain, and I'm Swiss. I also want to declare quickly my conflict of interest. I'm beside involved in DRYDEN Aqua, also involved in AquaSolar, which is a customer from Calplast for more than 30 years, yes. 35 years. I'm also, since a few years, I'm co-owner of Calplast as well as from Tara. So I have a conflict of interest. I want to declare it here, so don't trust what I'm saying. But we go today very deep in filtration and what you have to look in what details and how you can check if your filter does what we promise.
Yeah, and the point of today is really about the hardware of the filter vessel, and not a marketing for Calplast or Taro, but yes, we really want to be able to show what to look out for in your filter vessel, the hardware, the software being the media within the filter vessel.
Yeah, and we start briefly to recapitulate also a little bit on the software,
yep.
right? On what is filtration media, why, etc.
How it works.
And then we go deeper in the hardware, but we start briefly with this hardware.
Yes, with the hardware, we call hardware the filter, we call software the media. And inside the filter, what we have different components. We have the top diffuser, we have the media, and we have the bottom laterals or nozzle plate. All these components they are important so that the filtration works as expected.
Yeah. We'll see now. And I think what you said in the beginning is super important. Filtration is hardware, software. The filtration really comes from the filter media, the software, but you need a reasonable hardware that the software really can bring the best. And then the third thing, you have to know how to work with the software.
Exactly.
In the right thing. So it's a three-step.
Yes, and I think the first step is just to explain the principles around media filtration and how it works. So if we look at that very quickly, the main method of media filtration, that's all media filtration, is straining interception, the mechanical portion of media filtration, which really, depending on the porosity of your grain sizes, will trap the particles larger than that porosity.
Mike, what do you mean by porosity? You mean the grain sizes, right? So the smaller the grain size, the better will be this straining, this interception?
Yes, so it's more about the interstitial spaces between the grains than the porosity. Porosity is more about carbon and things, so it's the interstitial spaces between the grains. If your grains are smaller, your spaces will be smaller. So the smaller your grain size, the better your filtration. Okay. And then on the other side of that, if we look at how fines are removed throughout the bed depth of the media, that often uses sedimentation principles, where the vorticing of your flow allows for finer particles to settle in dead areas or low flow zones within your media, such as you see in the picture on the right hand side.
Oh, that's interesting. That's a little bit like in the river. If you go under a bridge, after a pillar you have a countercurrent.
Countercurrents, that's exactly it. So those are all countercurrents happening on the side, and your fine particles settle in that area.
Okay, here I have a question. The straining interception, that's more, let's say, a bit in the surface, if I understand it well?
Correctly, correct. Generally, it happens in the first 200 mils of your media at the top of the media. So because that clogs up pretty quickly, with the large particles blocking all of those gaps, so 200 mils is generally where most of it happens. And then the rest of the media is hopefully being used well for fines removal.
Yeah, but so sedimentation goes deeper.
Yep.
And then you have here also adsorption. Yes. I know absorption from activated carbon, where you have this huge inner surface where the particles are going in and stuck in this. That's good news, but they never come out.
Yeah.
Right.
So the difference of adsorption, so it's really add like plus and minus. Adsorption is where the particles adhere to the outside of the media surface, and that happens in two different ways. Either depending on your media's charge. So many medias have a charge density, mostly in the glass medias, and particularly our AFM standard, we have a very high negative charge, which means that we attract all the positively charged particles within the water onto the AFM very well. So it's used a lot for heavy metals removal from the water,
or together with coagulation.
Or together with coagulation, flocculation. So quite often in where you get a lot of colloids in your water body, river systems with a lot of fine silts and muds, those are all very similarly charged. And then you need a coagulation, flocculation process to distribute the charge densities more evenly between positives and negatives, bring those particles into larger form, which the media can then remove.
Yeah, what do you see here in this? So, but AFM-NG, NG stands for next generation. Well, that was developed from Dr. Howard Dryden together with his son Matthew years ago, mainly because of filtering out
microplastics and organics and lipids and fats.
Yeah, but mainly about microplastics, and then we found out, well, it also works very good with organics.
Yeah.
This is hydrophobic. Hydrophobic means what?
So hydrophobic, so you get hydrophilic, which likes water, and hydrophobic doesn't like water. So really, it's similar to oil particles in a water body. When they float to the surface, they all want to combine together because they're trying to get away from the water.
Yeah.
So we use that same principle with the hydrophobic media with all organics, lipids, fats, microplastics, which have a hydrophobic portion to their makeup that adheres and is attracted to the AFM-NG, and that's why we get very good 1 micron filtration performance.
But that means hydrophobic particles, you have to filter with a hydrophobic media.
Media, yes.
Okay.
Yep.
And that's what we are doing here.
Exactly.
And the AFM-NG is non-polar. There's no charge on it.
Yeah, exactly.
Okay.
Okay, moving on to the next slide, which I'll leave to you, Dominic.
Well, media filtration, we say there are 3 factors which are impacting it. One of them is the media depths.
Yeah.
What you see, maybe you can quickly show on the x-axis, you have the size of the particles from 2 micron to 100 micron, and on the y-axis you have the removal rate from 100% to 70%, how much you remove. And we have here tested with 20 meters per hour, or 20 cubic meter per square meter per hour. That's the same thing.
Yep.
We have tested the filtration performance of different bed heights.
Yeah.
Green is a 750 millimeter bed heights, where we got 1 micron filtration.
Yep. At 98% removal efficiency.
So even better than the 95, but usually at 95, at 500 millimeter filter bed, we got to 3 micron. And then with 250, you see we are 15 micron. So it's a big gap.
Yeah.
And this is why we always recommend to stay, if possible, in a filter bed of roughly 500 millimeter of the main media, so grade 1 or grade NG. To be fair, if you slow down the filtration velocities, especially in gravity filters where we have 5, 6, 7, 8 meters, then this difference becomes much less. But the higher the filter bed, the better is the filtration.
Particularly of the fine particles, which we're looking at, yes.
Impact number 2.
Yeah, impact number 2, filtration velocities. If we look at how fast your water is being pushed through your bed, so again, it's per square meter, cubic meters per hour per square meter. We did testing of different flow rates. If you look at the bottom, again, it's also the particle size band between 2 microns and 30 microns in this case, and percentage removal of 65% up to 100%. At 5 meters per hour, we pretty much achieve 99% removal of anything greater than 2 microns. At 10 meters per hour, 98% removal of anything greater than 2 microns. And then at 20 meters per hour, which is sort of getting close to our cutoff, we are removing around about 97, also around about 97, 98% removal of 2 micron particles. And then, just to prove the point, that filtration efficiency drops off the end of a cliff. Once you start getting higher than the 30 meters per hour, 25 is really our cutoff in aquariums and aquaculture. Swimming pools, I know, quite often uses 30 meters per hour.
That's the standard, yes.
Yeah. The standard is 30 meters per hour, and then you can see here at 40 meters per hour, your efficiency drops off dramatically. 60 meters per hour, even worse so. Your particle removal efficiency rates. So the reason why we always do a recommendation on filtration velocities is there because of this kind of data that we see.
Yeah, and this, ladies and gentlemen, is now with AFM-NG.
Yes.
You know, if you would compare these with a very good quartz sand, you know, at 20 meters, that would be, for us, the gray line would look like the dark blue line that you show here. So it's a huge difference, right? Yeah. This is, so what that means, you know, with AFM-NG, you can double the filtration velocity and still have I make it black and white, still have the same filtration performance. But that's not really what we want, right? We want to have the best filtration, especially in a one-pass filtration.
That's correct, yeah.
Like drinking water or pre-treatment before RO.
Seawater intake systems.
Seawater intake.
Many different applications that have a single pass.
And especially if you can't use coagulants and flocculants, you know, where you can, make it better just with chemicals. But if you can't do that, water intake, then...
and also our ethos is to reduce the usage of chemicals throughout the system. So, preferably not.
Good. Number 3, water hardness.
What is the impact of this? Water hardness is a bit surprising. The previous one, we could expect that they have some influence on the performance, but not the water hardness. We see again in the axis the particle size bands, and we see 2 charts. One with a standard hardness with 150 ppm.
Quickly for the audience, for those who are more familiar with French degree or German degree, that would be 15. So divided by 10, then you have 15 French degree, which would be roughly 9 German degree.
And also it's 150 milligrams per liter.
Yeah.
For those that work in milligrams per liter.
And we compare this chart with the one with really salt water with 23 ppm.
So that would be 22 French degrees, 1 German degree.
Yeah.
So there is a big impact in the filtering performance depending on the hardness of the water.
Yeah, and again, this is done with AFM-NG.
That's correct.
If you would see this with AFM standard or with any sand or glass media, you know, the blue line would just collapse down to 10 micron, if not lower.
Yep.
So really the NG is the only media which can handle soft water pretty well without any addition. I mean, all these waters you can harden up, you know, with calcium chloride, or talc is also a good one that you can use.
Being used more and more.
So talk to us. We have some how we can help this, but the softer the water, the harder to filter.
It is to filter. That's correct. Just a general rule. Yep.
Mm-hmm. Well, here we come to backwash, and filtration is always a 2-step process. One is to collect the particles, that's filtration, and then you have to backwash it. You have to release them completely, and therefore you need bed expansion, and therefore you need fluidization. Maybe Mike, you can let run here this video. You see here on the right side, you see a video. This is a filter media from Astral called Astral Active Clear Glass. 0.5 to 1 micron, and Matthew in his lab, he's backwashing starting from 30 meters per hour, and he's ramping up this to 60 meters per hour. You will see end of this video, you know, that we have 10% bed expansion from 1 meter to 110. But what you also see, you know, that this picture is not changing. You don't have fluidization.
Yep.
What is fluidization? Fluidization is this dance between the particles, you know, where they rub off the particles, which release the particles. And this is absolutely important that you have this. Now we are on 60 meters per hour, and you see it's a little bit of movement. It's bad expansion, but it's no fluidization.
Very little, yeah.
And why do we show this? Because in the DIN norms, they tell you need 10% of bed expansion to have a good result, and we disagree with this. We say you need minimum 15, ideally 25, or the higher the better. So we took here 15 or recommended 20 to show, with what media you need what backwash velocity to get to this recommended 20% of bed expansion, where we can assume you have fluidization. Mike, do you bring us through this?
Sure. And so, with the AFM-NG, because of its hydrophobicity, it's slightly lighter than many of the other medias, including our AFM standard. So it reaches 20% bed expansion at 30 meters per hour backwash velocity, and really good fluidization.
What would be AFM standard?
So AFM standard, we're looking at slightly higher. Our recommendation is 40 meters per hour at minimum.
Yeah, but you have it with 35. You also have this.
We do, but we like to recommend the 40 meters per hour.
Yeah, in general, we always want to have as high backwash velocity as possible. Your backwash process just becomes a lot more effective. Maybe you think, it's a little bit counterintuitive. You think the lower the backwash velocity, the less water I use. It's just the opposite, ladies and gentlemen. And we explained and we discussed and we proved this in our webinar number 5.
5, that's correct. The water treatment webinar.
So go in this and watch it. And if not, you just believe us. It's really in backwashing. The faster, the better. You need it fast and strong. And then you will save water because you have higher lifting forces than the drag forces.
If you don't have a proper expansion, no matter how much time you spend backwashing, you will never get rid of the particles.
No, never.
And there is a rule.
You always get rid a little bit, but never of all.
But yes.
What is the rule?
Yeah, there are some rules out there saying that you have to backwash 2 times the velocity that you use in the filter, which has no sense.
Oh yeah, that's true. That's what you're mentioning. That somebody put this into the industry. Backwash velocity must be twice the filtration velocity, and this is nonsense. Sorry to say. And we proved this. Here we proved this really in the webinar number 5.
I think the only place that can really work is in the swimming pool industry, where they're generally filtering at 30 meters per hour, right? But then you double that out, and then you get 60. So maybe it was a swimming pool engineer that came up with that idea.
No, it came from water treatment.
Oh, really?
In pools, we are much less good than the water treatment. But in backwashing, we are pretty good.
Yeah.
Usually, we are backwashing 50, 60 meters in public pools.
Yeah. Oh, well, okay, great.
We are better than water treatment. Sorry to say. But coming back, we have with AFM, we have 30. Swiss sand, which is also German sand, the best quality sand we ever tested. You're just above 40 meters that you need.
Yep.
Same grain size, by the way.
Same grain size,
0.4,
exactly.
0.8.
Yep.
It's just because quartz sand is slightly more heavy.
It's higher density than
Dutch sands from the Netherlands, not from Denmark, from the Netherlands, 57. Okay, slightly bigger is 0.5 to 1, but you see what big impact this has, and probably also the shape. I mean, what we take out from this is also that sand is not sand, right? There is a huge difference in filtration performance, but also in this backwash efficiency.
It very much depends on the mine that it comes from. I mean, the efficiencies can be totally different.
Yeah. And then we have 2 glasses here. One is this blue Nature Works, bigger than 65. And then this ACG, this is this active clear glass. That's what you have seen here, bigger than 75. Ladies and gentlemen, you never have more than 60 meters per hour backwash velocity. You never have this. I've never ever seen it. That means you cannot backwash this. And if you want to have a good advice from my side, go with AFM, the best, or stay with high quality sand. There is nothing in between.
Yep.
High quality sand is the second best.
Great.
Good. So now we ended up with the hardware.
We have the hardware now. We will group the filters into 3. The first will be horizontal filters. We call it the pore option. Due to the geometry, we will have dead areas everywhere in the corners. These filters has a belly.
Like me.
So we have the areas in the ends and on the sides of the filter. Then we can have, in these horizontal filters, we are limited by the diameter for the media, that height that we can use.
Yep.
Then we can go for vertical filters with laterals. We have two options: the pore option with shallow bed depth,
Yep. Very short filters,
and higher depth, which are better. But we always can have the option of nozzle plate, where we have normally a better distribution, but we will see the details afterwards.
Yeah, equal distribution, and also what is to mention, if you want to backwash with air, an air purge, you need a nozzle plate. Never ever use a lateral configuration. But yeah, I mean, horizontals, they're great because they have big surface, but on the design, they are very, very challenging.
Yeah, and we'll get into more detail of that later on.
Yeah.
So one of the components we spoke about in the beginning was the top diffusers. We must check that the components that we install in the filters, they work. So we have checked and tested different diffusers in the top.
Sorry, what does work mean to you? So
what do you want?
What do you want? What do we need?
Good point, yes. We need that the surface is flat. I mean, we need that the water...
Flat filter bed.
The surface of the media.
The surface of the media is flat, so we don't have a hole, we don't have a crater, and this means that the media will go evenly through all the filter media. If we don't have this, just the example that if we can have on top of the media anthracite or sand, for example, if we have a hole, we will not have this active carbon in the middle. So the water will go directly to the sand or the AFM, which is not a very good idea, and is not what we want. Okay,
but what you're saying, responsible for a flat filter bed is really the top diffuser.
Yeah.
And you checked other diffusers, like the Koenig, they are great for backwashing, but they give this turbulence where you get these mountains. Other ones which give this hole. The ones that you're using, they are guaranteed that you have a super flat filter bed, and you, ladies and gentlemen, you can check it if you have a sight glass.
Yep. Every filter should have a sight glass where you can see what's happening to your bed, to the surface of your bed.
As a manufacturer, we also fight for every millimeter that we have in the filter. We need to put the top diffuser in an adequate height so that we maximize the media height that we can have inside. Or we have more space for percolation before the water gets into the media.
So what you're doing is what we see here on the right. Why are people doing the one in the left?
That's because, it's easy not to think and to install. These are very easy to install.
Easy to install, and the other is not easy to install.
Not that.
Good. I do not mention that I forced them to put it on the right. Okay, let's go to the next one.
And this comes very much from me. It's a little bit of my bugbear, where unfortunately I see a lot of these very short filters being used in the aquarium and aquaculture, zoo industry, with the multi-port valves on the top. The reason why they're a bit of my bugbear is really they are very dependent on where the laterals can be put into these filters. Also, the laterals are generally quite short, which ends up with a very poor distribution of backwash, and resulting in dead areas around the sides of these filters. But not only that, with having such a short filter, you've always got to make space for bed expansion. Like we said earlier on, you need 20% bed expansion. So in often cases, that means that you can only get a maximum of 350 mils, and I do have many filters out there that's less than that of filtration media, which would be the grade 1. So our recommendation, and these are exactly the same diameter filters, so your surface area is the same, but to facilitate very good filtration, both surface filtration and deep bed filtration, where we're really utilizing the sedimentation phases throughout this deep bed filter, you really should go for a higher filter. So it's a deep bed filter and deep lateral position as far as down as possible, and like Yasura says, that allows for maximizing the filtration media.
Filtration is coming from filtration media. Huh? If you only have 50 kilograms in or 200 kilograms in, that makes a difference, right?
We always love the 200 kilograms.
Yeah, absolutely. That's also from a commercial. All three of us, by the way, are fathers. We have to feed the family.
Yeah.
So, no, but I mean, also out there, you know, in these zoos, you know, I think your animals, your fish and your animals, they deserve good filtration. And therefore, you have to invest a little bit in your
and it's
hardware.
not only the good filtration, it's that all these dead areas facilitate areas where parasites and viruses can breed, right? So you really want to avoid all the dead areas in your filters as much as possible.
The left one is not a good choice.
Not a good choice.
Very bad
not
choice.
a good choice.
Very expensive choice in the long run.
In the long run, very expensive. And the multi-port valves are not sized correctly, so their pressure losses are often very high, and you cannot achieve the backwash that you require for these filters.
Mm-hmm. Okay. Laterals. I heard that the laterals is a big story.
Yes, it's. Yes.
For equal backwashing, right?
Yes, we want an equal backwashing in all the surface. This option of a star in the bottom is very popular, and we say that they work okay up for diameters up to 950. Above that, they simply don't work. We have a big dead area in the corners of the laterals.
The pizza slices?
Yes.
Yeah.
The more the better. But we will always have some
What do you mean
space.
the bigger the slice, the better, or?
No, the more slides that we have, the better. The dead area will be smaller.
So more laterals to reduce these pizza slice sizes.
Also, if we have a big diameter and we keep with this design of a star configuration, we will have very long laterals, and we will see later that they are not also
they don't work
the best
at all.
option.
Okay, great.
Okay, this is a video which I got from a customer from Veldana, and they bought at that time these red filters. They are not manufactured anymore, therefore we can name them. And you see a beautiful red filter, and they asked
really
them to
good looking filters. Yeah?
Really good looking filters, you know, good. And they asked them to make them a big side glass in so they can show the AFM. And can you play the video?
Yep, sure.
Here you see the video in a backwash. You know, now they are backwashing this filter. This filter has a diameter of 640 millimeters, so it is. And now look where you have movements of the media. Here, in 30 or 40 centimeters, not more than this. So they sent me this video and said, Dominic, what's wrong here with the media? I said, well, I guess there is nothing wrong with the media. I came to you, and you said, yeah, Dominic, this is clear. This is because of the lateral configuration. They haven't done it the right. And I asked you, can you do it the right way? And you said, we are always doing it.
Yes.
Right?
Yes.
Give me the other video. So he took a normal cold blast filter, you know, with the normal configuration. The only thing you put in big side glasses.
Yes, we put a big side glass, and we can see here that the backwash is even in all the surface.
No, it's completely even. It's not just even. It's completely even.
Yeah. We have a proper expansion.
Look at this.
That's beautiful. Right.
It's the same diameter, 640.
Yeah.
The 640.
The same everything, yeah.
And this is just because of the lateral configuration. Now, ladies and gentlemen, if you would have asked me, is that possible that you have, because of the lateral configuration, not even distribution? I would say yes, you know, if you have filtered 2 meters, 3 meters, but not in 600. So I really was shocked. That was an eye-opener for me to see that you can have these problems, these huge differences in small filters.
So what does that tell you is very important?
It's super important, and you will give us now not all the secrets, but some of the secrets, how to do it right, or what's the problem.
But of course, you would never have seen that unless you had a sight glass.
Yeah.
So it's vitally important to have sight glasses in your filters.
Yeah, if you want, you need a sight glass.
Yeah.
By the way, in cold blast, all our filters have sight glasses.
Yeah.
You can't get it without
and
sight glasses.
as well?
In Torah as well, yes.
Yeah,
that's
the marketing spiel. Yeah.
No, it's kind of our DNA. We want to be the best, and we know how important it is. And yes, it brings the price up by, I don't know, 500 euros. I don't care. If you don't have this money, you're not our customer.
Yeah, because you've got to have the good hardware and the good software together.
And you have to control it, how you want to operate it, how you want to check it.
Yeah.
But let's go back to what we have seen. What is the difference of this red to the blue?
Yes, okay. We see in this picture that we are on the left, we see the laterals, they are very short. They are too short for this diameter, so we are not covering the surface. So the water is just coming up through the middle. We have this filter of 600, and we have the same configuration that we do in Calplas with long laterals that will reach to the corner, to the walls of the filter. In bigger diameters, we are not very friend of this configuration with a star, because we have a big.
So bigger, that means bigger than 1 meter.
Than, let's say 950, 1 meter. Yeah. Above that, the area are too much. So we need to go a more complex configuration. In fact, the bigger the diameter, the more complex configuration that we will have.
Yeah, and we'll see that detail a little bit later.
That's the configuration for a filter of 1 meter, 1.2. If you go in a 2 meter, then it's much more complex.
Yes. Yeah. And then, of course, as with all filtration, if whatever you're removing, whatever you're filtering out, you need to remove during backwash. Otherwise, you have a residual load which will build up over time, and your filtration will collapse. That speaks very nicely to this slide, which we've taken 2 filters, 640 ml diameter with a flow rate of 7.5 cubic meters per hour.
So Mike, this is exactly what we have seen before.
Yes,
Green
exactly.
is the blue filter.
Yep.
Red is the red filter.
Exactly.
640.
Yes, and so when you're utilizing the full surface area of your filter, 640, you've got a surface area of 0.3 square meters, and your flow velocity is 25 meters per hour, which is sort of our limit in aquariums that I normally recommend. Whereas with that red filter, as we were showing there, we've given it 400 millimeters, but I must admit I think it's less than 400, but we're being generous. With all the same flow rates, the surface area is 0.125 square meters, which means you're trying to filter at 60 meters per hour filtration velocity. That's just, it can't work, particularly in an aquarium and aquaculture with soft organics. Those just get sheared right through the bed, and your filtration does not perform.
In anything, I mean, yeah, AFM still will work in this filter. Will still work a lot better than sand. So that don't take me wrong, but you will not get what you could get out of a 600 millimeter filter. You pay 600, you get 400.
Yeah.
Yeah, from one side they look the same. Yeah. But they don't perform.
Yep.
Yeah. So yeah, that's a very important message, is that you're paying for the 640 mil, but you're actually only getting 400 mil.
Yeah. But you think you have a 600, so the system is not working as expected.
Yep. Okay, then I have seen this, and I really like that on shows where you had two levels of
double stack.
Yeah, double stack. That looks really sexy.
Yes, we have to start one above the other, because we try to minimize the dead areas that we have in the standard star configuration. They seem a good idea, but they are not. At the end, they are not a very good idea, because when you backwash, all the flow comes out from the top, not from the bottom star. So we have dirt generally accumulating in the bottom part. Yeah. So in the end, it's even worse, because we reduce the depth height.
Yeah, you reduce the depth height, you've increased the bottom section for building up of biofouling and dead water. And so your pizza slices are still there, even though you think you've got rid of them with the additional star below it.
So no double stack laterals, that's the message. No double stack
laterals, yeah.
Okay, but let's go for nozzle plate, because when you're nozzle plate, you're always super safe, aren't you?
You are not. You are not.
I mean, first of all, nozzle plate, we mentioned it before.
Yes.
It's always better than laterals. You're always on the safer side. And if you have nozzle plate, you can backwash it with air. That you cannot do, once again, with laterals. But give us a little bit of details.
Yeah, we can have this configuration that we see here, when we don't have a space on the sides to put nozzles, or we can put nozzles shorter that we see later. But here we don't have a proper backwash on the side, so we will have the same effect as before.
So because they are laminating in, and then you can't place...
There are different reasons. One of them is that the technology that they use, they build the nozzle plate outside, and they fix it, they glue it, or they laminate it to the walls So they need this space for gluing the.
So you lose there 10 centimeters.
You lose 10 centimeters, which in a filter of 600 you are dead.
Okay.
Or we don't have much space on the side, but we can still install a nozzle, but shorter than the previous ones. So all the air will go through this nozzle from the corner.
Okay, in water that would not be such a problem, that would be pretty okay.
Yeah.
But with the air wash, you know, if one is shorter, then you destroy your air wash.
Yeah, this is very important when it comes to air backwashing, but with water not so much.
Good. I think that's a good one. You know, left we see cold blast property sign, you know, out to the end really, and then on the right I don't know what the brand is, but very obviously you see here we have more than 10 centimeters we are missing.
Yep.
And then even in the middle you're missing again.
Yes, both filters has a diameter of 1.2. We want a velocity of 20 filtering, so we use a flow rate of 24. In case of on the right, we have a flow rate of 24, but the actual diameter is 1000. So the filtering surface is reduced from 1.2 to 0.8. So the velocity is 30. I mean, we are increasing 50% the velocity, and we have seen in the first slides how the performance comes down dramatically.
So that's again the same thing. You're paying for 1 meter 20.
Yep.
You only get 1 meter.
1 meter. Yep, same thing.
Good.
Yeah.
Or not good.
So here we can see a proper design of a nozzle plate. We have an even distribution of the nozzles. They come up to the wall. We need at least 60 nozzles per square meter, and we can see a proper backwash with air in this video.
Yep, there we go.
So that's typically cold blast, typically Gesura.
Yes,
you're testing everything.
Yes, we need to test everything.
Yeah.
Yep, to make sure it works according to the design, right?
Yeah. Ah, very nice.
Great distribution.
Great.
Yeah, very good.
Okay, but you're not testing only nozzles, right? You're also testing laterals.
Yes, we test laterals. We said before that especially long laterals, they not perform as expected. We have different slots, and the longer the lateral, the more problems that we will have. So here we have a picture of a lateral.
Why is this?
This is that the water has space enough to go out from the last bit. The water has some speed, and it keeps the same speed, and this speed will be used to come out.
So it goes to the end, stops there, and this is why it's spraying just in the end.
And it's capable to go out only through these 5 holes which are in the end. If we modify the hydraulics and we close the holes and we make smaller holes, we can have an even distribution. But this is very difficult to do, and you don't normally do it as a general rule.
So, ladies and gentlemen, what you see here on top, that's what you usually get.
Yep.
If he treats it, he can cheat it and rework it that you have the one below, but usually it's not what you have. Learning, we want not to have long laterals, right? And you need the right speed. We don't go into details in this because he said you want to keep this as your secret.
Yeah.
There is some logic behind. What do we see here?
Here we see what we want. We have a filter diameter of, let's say, 1.2, and we want an even distribution of the water coming out through all the lateral. And here is what we expect to have, and here is what we check and we test in Calpras to know that we have a proper backwash.
So how you're doing this, you make your calculation, and then after calculation you build a model, and then you check is your modelation, is your calculation working?
Exactly.
Good. Okay.
Let's move on to the K2 of filtration.
Yeah, because
right?
I said horizontal filters is the most difficult to build. It's the Mount Everest, and you said no, it's the K2.
K2, because the most deadly mountain.
Yes, yes. Okay, tell us.
Good.
Well, we have we saw before that yes, the horizontal filters due to the geometry, they have dead areas in many places, but also small changes in the design can make it better. So we have the classic configuration. We have example of the 10 square meter backwash of 50. So we will have a flow of 500. This means that we will have we will need to install a pipe of around 300 in the middle, from side to side, and this means that we will have a dead area of 300 in the middle.
So that's the standard design of most
Yes,
of the horizontal
this is a
filters.
classic
Big
design.
pipe below, big pipe above.
Yep.
Yes, we will have long laterals, but just take that into apart. We will have minimum the area of 300 in the middle.
Yeah.
If we just change a bit the design and we have a pipe coming to the middle, to the center of the...
So also we come in with 300, but then we
Yes,
split it in
split
2
it.
times 200.
225.
Yeah.
Then we will have the area reduced.
So that's already a much better design.
Yeah.
This is a much better
Is that the
design.
design you're using?
No, it's not. This is not enough.
Still longer laterals, as you can see in the picture below. The laterals are very long.
So we can have a different design where we have split the flow into 16 pipes.
What do you mean we can't? This is how you're doing and Toro is doing it.
Yes, this is how we do it, and we don't do the previous two. We don't do that because they simply don't work.
Yeah.
So we do this design where we have smaller pipes and the area is reduced dramatically.
So you also come in with DN 300
Yes,
and they
yes.
get smaller and smaller to compensate for
Yeah.
the pressure drop. Then you split it in 2, and from these 2 you go then for 2 lines with
Yes.
small laterals.
Yeah.
Yeah.
That's a lot of work. That's a lot of piping. That's a lot
Yes,
of...
it's a lot of work, but I mean design, but at the end we see that this is cheaper.
Yeah. So what you're saying, only with this you get the proper
The proper
performance.
performance, yeah. Both
Yes,
in filtration and
we have
backwash.
the filtration surface that we think we have.
Yeah.
Okay.
Okay. So if we look at that, many manufacturers out there have different configurations of their laterals installed. So some try to get as low as possible to achieve as much media bed depth as possible, and that's a good thing. However, just purely because of the roundness of your horizontal filter, that really compromises the length of your lateral, and therefore you have very big dead areas both on the sides and in the middle, as we said earlier on, above the big pipe. So going from a 11.8 square meter filter, you can often end up with only 7 square meters. If you bring that lateral higher up, you have an even bigger dead area below the laterals. You have a shorter bed depth, so compromising filtration performance of the fines, as we showed you earlier on. But then your laterals are also a lot longer, which we've shown previously also don't work as well. The worst case scenario is if your laterals are very high up in the filter and very short. That really can't achieve much filtration performance after the first few backwashes, because this surface area is really only the active surface area that you'll be using.
This is roughly
in a short space
half
time.
of what you expect,
Exactly.
right?
Yeah, roughly half of what you think you're doing, and because of that, you are designing for a flow rate of 11.8 square meters, but you're only using 6 square meters. So your filtration velocities are ridiculously high.
Yeah, and that's also impacting our AFM.
Yep.
Also, that performs much better than SAP, but it will impact the AFM. You're not anymore on the 10 that we discussed, or the 20.
Exactly.
You're double.
Yep. So this one is really talking about the long laterals again, and as Ursula said in the previous example, with your flow rate only coming out on the ends of the laterals, you tend to find situations like this where you have the dead flat surface in the middle of your filter, and then the clean surface area on the 2 sides where the backwashing is actually taking place, and those are the 2 small surface areas that's happening. The rest is all dead area for parasite and pathogen breeding grounds and poor water quality.
Well, that's very similar to what you showed before with the short laterals.
Exactly.
So short or long laterals, in effect, doesn't play.
You're in a difficult scenario either way. So.
Okay, what's the solution?
So
I'm interested in solution. Huh?
We have this on top. We have this configuration, which is classic configuration.
That nearly everybody uses.
Yes, and we are covering most of the surface. But we will go in deeply and we put some numbers there. If we have 10 square meters, we want a backwash of 40, so a flow of 400 is required. If we have 110 laterals, the flow per lateral will be 3.6. If we have a configuration of internal diameter of the laterals of 16, we will have a velocity of 5, which is huge.
That's very big.
If we change to the design on the bottom, 220 laterals.
So
the flow,
your design?
our design.
Yeah.
The flow will be 1.8. So the velocity in the pipe of 16 will be 2.5. We can see in the bottom chart that for 1.8 we have a head loss around 600, 700, which is perfect for a backwash.
Yeah.
This is what we want.
600, 800
Yes.
Yep.
millimeter.
Millimeter, yes.
Millimeters.
600 millimeters of head
Yeah.
loss.
Yeah.
If we go to 5 meter per second that we have in the top, we will have a huge head loss. And not only that, we are in the vertical part of the curve.
Yeah.
So that this means that we will have a big head loss with small changes of
Yeah, but this is
and
an
that also will
exponential
mean with
curve.
this high velocity, 5 meters per second, you shoot the water to the end
Yeah.
and it will spray just at the end.
Yeah.
Yes.
And because this is a exponential curve, the impact of your friction loss is dramatically
Yes.
larger the greater than 2.5 cubic meters per hour that you go.
But anyway, 5 meter per second is
It's just ridiculous. Yeah.
Okay,
Good.
Let's go on.
So we can summarize and we will put again some numbers to what we have explained. We have
Before you start, right, you see the concept Gulplas and Tara, because
Yeah.
you also make the developments for Tara.
Yeah.
And left is, we called it rest of the world.
Rest
I
of the
mean,
world.
what majority of all our other suppliers are doing, right?
Yeah.
Okay.
So we go for an example of a filter of 2.2 meters diameter and a length of 5.6 meters. So we will have a filtering surface of 11.8. If we want to backwash a 50, we have the backwash flow of 580, and the filtering velocity we want 20, so we will have 234. If we go to the design on the left, the rest of the world one, we will not have an area of 11.8 at level A. We will have 7.9. So the backwash velocity will be huge, 73, and
Which
the
is
filtering
good.
velocity
Yeah.
will be close to 30.
Which is
so
not
we will
good.
have 48% more than expected.
But previously you said high backwash velocity is good, so why would this one be bad, Hasura?
Yes, that's because this is not expansion, this is boiling.
Ah.
We will lose the media.
Yeah.
We think that the media velocity is 40 or 50, but it's 73.
Yeah.
So this is not what
And
we
it's
want.
centralized.
Yes. So you say all of the surface area that I'm showing here on the screen will be boiling up, and that's where we tend to see media loss.
If we go to our design, or the one on the right, we will have, instead of 11.8, we will have around 10.2. So we will have a backwash of 56 and a filtering velocity of 22.9, which is acceptable, and we have 14% more than expected.
Yeah. Well, life is full of compromises, especially horizontal filters, right? You have a little bit to compromise, but that's the very best you get out of this design. And yes, you will have no boiling. You also will have a little bit of loss of media in the beginning. That's the fines. That's the inch share, as I call it.
Yep.
That's okay. But it should not be more than 5%.
It shouldn't be continuous. It shouldn't be ongoing.
No, it
at
should
every
stop.
backwash.
It should stop.
Yeah. So I like this slide, so I'm going to take this one very much because many of the manufacturers, or actually all of the manufacturers, give you the surface area of the B level, which is the greatest diameter of your filter, to tell you that this is the design surface area utilizing, but nobody out there uses the B to install your media, because then your media bed depth is so limited that quite often your filtration efficiency drops dramatically. So they generally fill up to a level of A. However, the level A, as you can see by a dome shape of a round filter, is that your surface area of A is less than B. Therefore, your filtration velocities end up being higher. So the one thing to be aware of is to make sure that when you are designing your flow rates for a particular filter, to use the right bed height that you're utilizing, and that surface area at that bed height. that can be calculated by the help of your manufacturer.
In Tara and Coplos, we give always these 3 levels in the future. You know, that you as the engineer, as a specifier, can go and see what you want to specify. Of course, we also give B to be comparable. What do you see outside?
You need to be comparable. No, great.
No, but it's an important one. Okay, one about the connection, and that's for horizontal filter, but also for vertical filters. And here you see an example from an Lateral filter, very good filter, 2 meters in diameter. And these filters you can buy, you know, for 20 meters per hour filtration velocity, or how they say it, 20 cubic meter per square meter per hour. Or for 30, 40 and 50. And then you have a connection of only 110, or on the 50 you have 160. And ladies and gentlemen, please never ever use 110, 125 and 140. That's okay for filtering, but I guess from time to time you want to backwash this filter. It's not you put it in and you change the filters with the media. We want to regenerate, you want to backwash it, and then you need 50. And you absolutely cannot backwash a filter with 110 in a 2 meter diameter with 50 meters per hour. It's absolutely impossible. So please never ever use them. Go for these filters. These are good filters, but for the green with 160.
And filtering at a velocity of 20.
And filter at a velocity of 20. And for all the manufacturers out there, Astral and all the others, sell these filters with less than 160. That's not good. You know, that proves your competence, that you know filtration and backwash velocity are different. That was a little bit emotional, sorry.
Yes. But I can understand.
I really cannot understand it. It makes me angry.
No, I understand it for sure.
So we have concluded that we need a side glass. The side glass can be for different shapes. We have a very, very long one. We can have a circular one. We can have one on the top, or we can have a long one. But at the end, what we want is to check that we have a proper expansion and the media is
flat.
Flat.
This is why you need side glass, and you need good side glasses that you see through. If you don't see through, it's not a good side glass.
You will see out there some side glasses when they have not a very good design, so they have a lid outside. So there is media that is not expanding, so you cannot see what's going on inside.
Or you have some which are not really transparent.
It's not moving. And,
Let's make it short. You need a side glass that you can see through, and where you can control your filtration and your backwash.
For sure.
Okay, here we come to
the nitty-gritty. K2. How to solve K2 safely. So under Hosura's great engineering guidance, Tara has created a filter that I went to go and investigate to see how well it performed. We asked them to put in additional sight glasses so we can monitor the bed levels at all different points throughout the filter, and this is the video that we came up with. Sorry, it's not a professional video at this point in time. There are ones out there, but this is really to show the details of the backwash. So have a look at the video. Filtration performance, there you can see we were monitoring the different bed depths and the expansion capacities during the process. This was at filtration at 20 meters per hour. Just to make sure that the bed was not moving in any way and wasn't kicking up on the sides.
So the flat bed was super
absolutely flat bed. Then the first backwash was at 30 meters per hour, and you can see really great fluidization. We achieved the 20% bed expansion.
Equally through all over the surface?
Throughout the whole surface. Yeah, to the edge. And this view was actually from the side video, from the side window. So it showed that the overall bed expansion throughout the whole filter was great. Then at 40 meters per hour, you can see even better bed expansion and fluidization. We then bumped it up to 45 meters per hour. And this is a great video because it shows the expansion very clearly from the length of the filter, the window at the top end of the filter, and also that the whole surface is expanding very well and evenly, and the whole surface is also fluidizing. which, I mean,
super clear.
To achieve this in, let's call it the K2, is unbelievable, and we are very proud of Asura for the design and engineering works that he's done, and also for Calplas for Terra in the building.
Look at this, you know, how equal it is through all the filter bed.
Throughout the side.
Yeah, fantastic.
And then also to test, because sometimes we do heavy metal removals, and then we definitely want greater than 50 meters per hour. We also did a backwash at 53 meters per hour. And look at that great fluidization.
Perfect.
No loss of media, which meant that it wasn't just boiling in the center of the filter. And then during the slowdown phase, you can see where we were slowing down the velocities. You can see very evenly how the bed was dropping down into place. Ending off with a perfectly level bed again throughout the whole filter.
Well, you have done it, K2.
Yes.
Congratulations.
Yeah, well
I
done.
think it's very, we can't really enough appreciate, you know, this design. It's really super difficult to do that you have equal backwash even at 30 meters per hour, and then that you can play between 30 to 50, 55 meters per hour.
What a lot of people don't understand is that actually backwashing at the lower flow rates to get your expansion is far more difficult than at the higher flow rates. So it shows a really good filter.
How are other filters performing? We do not know. We can't tell you. You also please do not send us how is this filter performing. We do not know. You can know because you ordered with a side class, and then you make the same test, you know, and then you will see.
Yeah, and also just a quick review of the lateral design as per the drawings, or even looking into the filter will give you a gut feel. Is this going to, from what we've showed you, is this going to work well or not?
Okay, do we have one more slide? Or
just at the end, please follow us on all of the social media channels, LinkedIn, YouTube, and on our website we have a lot of download material.
On YouTube we have 3 different, one for pools, one for water treatment, and one for aquaculture. Some of them are similar. This video will be on all the 3 of these because it's such a very important one.
Yes.
For me, it was good fun. Thank you, guys.
Great. Thank you very much.
And thank you for your attendance, and hope to see you on the next webinar. Thank you.
Thank you.